Hello, my name is Larry Lapides. I'm with Imperas Software. I'm talking today about advanced RISC-V processor verification methodology. So we'll talk today about RISC-V and processor verification, sort of set up the talk here, set up the problem, talk about the RISC-V processor reference models, and then go into the verification methodology, provide a couple of success stories at the end, and then we'll wrap this up. So let's start here with RISC-V and processor verification. So RISC-V is why we're worried about processor verification right now. RISC-V is taking over the processor world, except for x86. And yes, I think that includes ARM. RISC-V processor customization means that every RISC-V developer needs to verify the RISC-V processor because every RISC-V processor has some customization. But the RISC-V processor IP vendors guard their verification methodology and details more than the IP itself. They put this behind the castle walls or the fortress walls because with the verification flow, someone could reverse engineer a high quality processor. So there are few public details about x86 or ARM or Apple, et cetera, processor verification. RISC-V freedom enables domain-specific processing. So here we've got the who, what, where, when, why of RISC-V. Now we see RISC-V users as including traditional semiconductor companies, but also embedded systems companies that are now practicing vertical integration by developing their own SoCs. So RISC-V is an open instruction set architecture. It is not a processor implementation. And we see RISC-V growing in market segments where x86 and ARM are not dominant. And this could be, for example, small microcontrollers for SoC management, could be vertical markets such as IoT and automotive, could be horizontal market segments such as security and AI, or even deep embedded applications. And we see now that RISC-V processors are now used in over 30% of SoCs. And it's this freedom, the ability to provide just the extensions that you're looking for to provide custom instructions. This freedom with RISC-V enables users to develop differentiated domain-specific processors and processing systems. So what are the keys to RISC-V SoC success? The first, of course, is the processor IP. This could be from the processor IP vendor, it could be open source IP. You could be building the RISC-V processor yourself. The second key to success is processor verification, because no matter how you build the processor IP, you're going to add custom instructions. And the third key is the software porting, development, bring up, and test. Again, all three areas need to account for the addition of custom features to the processor, because everyone adds custom features. So let's go back to this, provide just a bit more focus. So what we're talking about today is processor verification. This is where I'm going to focus. And success in processor verification requires a high quality model of the processor. So that's the next topic I'm going to cover. And then it also requires innovative technologies and methodologies, sort of the lost art of processor verification. And that's the second key topic I'll go through. But let's just start with looking at RISC-V processors and processor complexity. Here, what I'm showing is an Andes AX45 MPV. So this is a 64-bit multi-core in the RISC-V world multi-hart, which also has vector instructions. supports privilege modes and various other things. So this is a significant application processor. It's got a fair bit of complexity here. So again, RISC-V is a modular instruction set architecture. Any extension, an extension being a functional group of instructions, such as atomics or compressed or floating point or vector, can be added to the base processor. Then you start adding in interrupts, privilege mode, debug mode, multi-hart, and it gets really complex. And then you have to worry about processor verification and the toolchain development and other software development. So just looking at the processor itself has a significant amount of complexity. But then what happens with RISC-V is that a number of users are developing RISC-V based processing subsystems. So these are multi-processor subsystems for DSP, for AI, machine learning, for packet processing. And again, this adds even more complexity. So what I'm showing here is the Dolphin design, Panther DSP. This can be configured, I believe, from 2 to 16 RISC-V cores, depending upon the DSP processing power that is needed there. And then below that, this is the NSI Techs. They are a company in Japan, a Denso subsidiary. So this is for automotive. And this is data flow processor, so for AI. And here we've got scalar cores, multiple scalar cores that are feeding in a vector unit. And so what NSI Techs has done is taken advantage of this architecture flexibility with the RISC-V to do something innovative to get exactly the right optimal mix of processing power, small area, and low power consumption. So we have these interesting complexities in the individual processors as well as in these subsystems. So let's talk a bit about the processor models here and the model requirements. So of course, the model needs to support the ISA, including all versions of the ratified spec and the stable and ratified versions. It needs to model the other behavioral components like interrupt controllers. It needs to be easy to update and configure for the next project. It needs to be user extendable for the custom instructions. You need to be able to model the actual processor IP. There needs to be a well-defined test process for the model. I'm not talking about RTL verification here, but you need to have a well-defined test process for the model, including coverage metrics. It needs to be able to interface to other simulators, interface to software debug tools, interface to software analysis tools, including access to processor internal state. Most RISC-V instruction set simulators can meet one or two of these requirements, but we've been doing this for 15 plus years. We support not just RISC-V, but about 12 different instruction set architectures. And so as we come to this, we support all these requirements with the Imperas models and tools. So what are we talking about here with the RISC-V fast processor models? So the RISC-V models support the full RISC-V specification, the full alphabet soup here, including privilege modes. We have models of the processor IP vendors, and we're able to support developers that are building their own processor. The custom instructions are easily added by the user or by Imperas. This is done in a side file, so as not to perturb the verified model. And models are built using a test-driven development methodology. So tests are built at the same time the features are added. There's a continuous integration test flow. There's around 18,000 tests that we run when our developers check in code. And then if we're building models of processor IP vendors, then they're also helping us to validate the models. This is the architecture of the reference model. So there's a base model, there's the configuration parameters, there's vendor-specific configuration, plus any custom instructions that the vendor has, and then there are the user custom instructions here. These are all built with the same set of APIs. Those APIs are supported by the Imperas simulator. So this all looks like a single reference model. So we're supporting the full RISC-V specification. It's user configurable to select which extensions and even which version of each extension. The base model is built, again, using this test-driven development methodology. And for the custom instructions, again, they're added using the same APIs as the base model. So actually, any of the tools that we've built here are going to work the same for the custom instructions as they do for the base model. And this happens automatically, no additional work needed. So with this architecture, this RISC-V base model gets used in all Imperas RISC-V processor models. So commercial users, academic users, users of our free RISC-V OVP Sim Plus instruction set simulator, they're all using this reference model. They're all using this base model in particular, which means this base model gets used by over 150 different organizations. It's very well tested. It's proven by use in fire. The other thing about the models is that they can drive the customization. In the RISC-V world, custom instructions are added to optimize a specific application or set of applications. Models are much faster to develop than the RTL, and there's better profiling information available. And so you can start by characterizing the algorithm or the application. You can do that by simulation of this application using the RISC-V model, analyze the results, add custom instructions, again, looking at this full RISC-V model, and then continue to iterate here. So the models are a very good methodology for adding the custom instructions. So let's move on now to the processor verification methodology. If we look at processor verification, there are effectively 5 levels of processor DV methodology, starting with just getting hello world to run. There's some self-checking tests, post-simulation, trace log file compare, and then synchronous step and compare, asynchronous step and compare. I'm not going to go into detail on all of these. Let me focus instead here on just the post-simulation trace log file compare, and then the asynchronous methodology. So with the post-simulation trace log file compare, this is a fairly straightforward process. It's just running the same tests into both the RTL and the reference model, getting a trace log file out, and then doing the comparison. And then this is supported by using the Imperas RISC-V OVP Sim Plus instruction set simulator, and typically the RISC-V DV instruction stream generator, the test generator, open source from Google Cloud or CHIPS Alliance. The asynchronous continuous compare methodology looks a little bit different. Actually, this is a co-simulation methodology where the same tests are run effectively simultaneously in the RTL and then in the reference model. So here, asynchronous events are driven into the device under test. There's a tracer module here that's part of the RTL, which informs the reference model about these asynchronous events. And then the verification IP here handles the asynchronous events, handles understanding what is going on in the RTL. And this asynchronous continuous compare methodology is needed to support features such as interrupts, privilege modes, debug mode, multi-hart, multi-issue, out-of-order pipeline, all these complexities. So just taking a different look at this, here we've got the reference model subsystem. The RTL is here. Here's that tracer module, and this is built using the RVVI RISC-V verification interface. It's a standard interface for talking between the RTL and the reference model. We see the reference model itself here. There's a bunch of verification IP. There's actually functional coverage modules here. There are directed tests as well as an instruction stream generator here. And then last, there's the debugger. And again, having a methodology, a flow that looks like this to handle the asynchronous events is needed to support the complexities in the RISC-V processor. So let's go into a bit more detail on some of these components. On the verification IP side, we've got verification IP both in system Verilog to move the data between the RTL and the C reference model. And then we've got the C-based verification IP as well that's handling the configuration, the synchronization, dealing with pipeline synchronization, and then the scoreboard and pass-fail. This is the RISC-V verification interface. This is the standard interface for communication between the RTL and the C reference model. So here we have the RTL, here we have the two components, RVVI trace, RVVI API that are available for this. So this actually works very well and is available on GitHub. It's work that has evolved over the last 3 years of Imperas working with various partners on these standard interfaces. The next component of the verification methodology is functional coverage. So thing with functional coverage, there are a lot of instructions to cover. If we just look at 64-bit RISC-V and we start adding up the number of instructions, and actually I think there are some things that have been left out here. We're close to 1,000 different instructions. And then for cover groups and cover points, you start looking at 10 to 40 or 50 lines of system Verilog for each instruction. And so very quickly, we're at, 10,000 to 40,000 or more lines of code to be written for cover groups, for cover points. And this is not design or course specific, so we haven't gotten into cross coverage or anything like that. This is just the basic functional coverage that is needed. And so what we've done at Imperas with RISC-V ISACOV, this is automatically generated system Verilog functional coverage. So we've built a coverage code generator here, and it supports the full RISC-V specification. It's providing functional coverage of instructions and operands. In the near future, we'll be adding support for CSRs and data hazards. We can support custom instructions in this. But the idea is that instead of users having to write 50,000 or more lines of system Verilog functional coverage just to get started, we take care of that grunt work. We take care of the repetitive stuff and let you focus on the things that are key to your design. So as I mentioned, the functional coverage is written in System Verilog. It works with any of the functional coverage tools that are out there. And here we're showing the functional coverage results in Synopsys Verde. So RISC-V Isakov and the rest of the Imperas DB flow work with any of the System Verilog simulators. Test stimuli is another key piece of the DB environment. Usually, you're going to be using an instruction stream generator and/or directed tests. The instruction stream generator generates test programs using effectively a constrained random approach. So this could be a commercial tool such as Valtrex Sting, could be an open source tool. It's going to require tool chains, and of course you need functional coverage so that you know what you've tested. Imperas also has directed tests. We've developed a directed RISC-V test generator, and we've got instruction coverage verification IP and a mutating fault simulator to make sure we're providing high quality test suites. So what we're providing here are two things. One are architecture validation test suites. There are over 50 of these for RV32, RV64, and then the basic instruction sets. And these are available at no charge at this GitHub repo. And then we've also got commercial directed test suites for the vector extensions and for protected memory components. Last element of the DB flow is the debugger. The Imperas multiprocessor debugger is an Eclipse-based debug tool. So you can do source line or instruction level debug. You can see custom instructions in this. Works just fine. And again, the debugger and the analysis tools automatically work with the custom instructions. So here we show the custom registers for custom instructions in the debug environment. And here we're actually showing custom instructions in the trace disassembly. So debugger, the tools automatically work. One last thing here, not part of the RTL simulator DB flow, but as you get to more complexity in the processors, you also want to use advanced techniques such as hardware-software co-verification, using hybrid simulation and emulation. That's where tools like Palladium or Protium from Cadence come in, or similar tools from Synopsys or Veloce. Here we're showing Cadence. We actually have an OEM relationship with Cadence so that you can get Imperas RISC-V models and simulators directly from Cadence. So there's the virtual platform in the Cadence Helium environment connected to the Palladium or Protium FPGA prototyping tool or hardware emulator. So that's the methodology side. Let's talk a bit about the successes here. So this is the open hardware Core 5 Verif. So this is effectively that same methodology that I've shown earlier, but this is now translated, if you will, to the open hardware terminology and from their slides. So the open hardware users are now on the third generation of the Core 5 Verif DB flow. The CV32E40P has been successfully taped out, actually in a number of SoCs. And then there are four processors: the CV32 E40P V2, the E40S, E40X, and the E20. So four that are all using this flow today. All are expected to complete DV and be taped out in SoCs by the end of this year. And then there are other successful DV projects using Imperas, including Codasip, MIPS, Nagravision, NSI Techs I mentioned earlier, NVIDIA Networking, the Mellanox team using Imperas models and tools for design verification. So let's wrap this up. I mentioned before that DV is one of the closely held secrets, but actually what we're trying to do here is to provide you with the key to the RISC-V castle. The asynchronous step and compare methodology using high quality reference models using verification IP, verification standards, verification metrics, and that's what Imperas DV is providing for RISC-V processor verification. Thank you very much.